boiler efficiency and the boiler fuel cost actually accounts for 2/3 of the total energy cost of the plant.
Sure.
When people set up plants, the emotion is largely bullish.
Would it make sense to then buy bigger boilers which have higher heat transfer area?
Connection between heat transfer area, water holdup, and efficiency isn't true.
You have an air preheater or a water preheater, you have an economizer. But do they really pay back in terms of what we do in terms of investment on such white elephants?
Hundreds of boilers that are connected, their own algorithms with a self-learning basis so that boilers can run themselves.
I welcome you all to the podcast FM Energize, which is on the topic of boiler efficiency and its impact on sustainability. With us, we have Vivek, who actually handles the boiler business for Forbes Marshall, and we would look forward to his insights and thoughts on this subject. So Vivek, just to get to a connect, if we look at the overall need for the process industries is to look at carbon footprint reduction and operating costs being lowered. So what do you think is the role of boiler efficiency in impacting these two important parameters for process industries?
Thank you for your kind introduction, Vaibhav. Yeah, it's a very vital subject and at a center stage of every conversation when it comes to energy reduction and carbon footprint reduction. Every plant we almost visit, customers would ask the question, oh, how do I improve my boiler efficiency?
Right?
And why so? Because boiler efficiency directly impacts their fuel cost. If you see for a typical process plant, boiler efficiency and the boiler fuel cost actually accounts for 2/3 of the total energy cost of the plant.
Sure.
So 2/3 is the fuel cost and another third is electrical cost. And that directly impacts the profit line, profit margin of their business.
So if you look at this statement and we say that two-thirds is contributed because of the fuel cost, the first question which would cross anybody's mind who's looking at buying a boiler would be, how do you really size a boiler? Because there are various scenarios which happen in a process plant, like should I size a boiler which is apt for my current steam consumption needs, or should I be slightly futuristic and plan for a couple of years ahead? Let's say if the midterm view is like 3 years. What do you think should be the right way in which we should approach this whole subject of boiler sizing?
Very interesting question. If you see decisions for capital investment are not taken solely by technical people, and for the right reasons, because there's capital involved. So
Absolutely.
it's always a techno-commercial reason why something is purchased. Now, when people set up plants, the emotion is largely bullish, which means
Absolutely.
people would say, I want the best, I want the grandest. And so they would say, my expansion, my future plans are, my plant would become 3 times, 5 times over the next 7, 8 years. And a typical life of the boiler is about 20 years.
Sure.
So in this horizon, people tend to oversize the boiler and you underplay the losses in efficiency that you have because of poor capacity utilization of the boiler. And when we walk through industry and plants, we see boilers typically operate at 40%, 50%, 60% of their capacities. And that's where we see the gap between the rated efficiency and the actual operating efficiency, which is wide apart, as high as 15 to 20%. And if you see in a life cycle cost of a boiler, about more than a half is fuel cost.
Okay.
And capital cost based on the type of boiler, whether it's oil and gas or solid, would actually vary between 15% to 25, 30%. So all these grand plans actually eat into your costs as you start operating, because while you would have envisaged that the boiler will be, my plant will go 2x, 3x in capacity over the period of 3 to 5 years, we end up the plant operating around at the same levels or incremental levels of 10, 15% over the next 3 or 5 years. And you end up having a white elephant. And I'm using the word white elephant because
Yep.
it's high on maintenance, it's high on operating cost, and it just drains. So it's a poor decision to actually invest considering future capacities. You should actually, at best, have a medium term horizon in place.
Okay.
You should invest for capacities which are 3 years out and try to operate boilers between as low as 60% going right up to 85, 90%. The sweet spot being between 80 to 90% of capacity utilization for best efficiencies.
Right. So if I get your thoughts right, then you are saying that 50% of energy is spent in the form of fuel to really look at the operations of the boilers over a year. If we go by that basis, do you think that we should run boilers at the lowest possible pressure because that's where the fuel consumption would be the lowest?
Yeah, that's another myth which needs to be debunked,
Oh, is it?
because people believe that if I raise the pressure means I'm spending more fuel.
Absolutely right.
If you take some numbers, if you take boiler energy and steam at 10 bar, it's about maybe 663. And
Sure.
if you take energy at 5 bar, it would be 662.9. So it's in so much decimals that you can't even account for the difference between the energy in steam at 10 bar and the enthalpy of steam. Energy and steam, I mean the enthalpy of steam at 10 bar versus 5 bar. So
Sure.
absolutely there's no difference in actually running a boiler at 10 bar instead of running it at 5 bar. In fact, it's the reverse. If I run the boiler at 5 bar, which is lower pressures,
Right.
I end up generating a lot of wet steam because steam expands at lower pressures. Your
Sure.
specific volume is significantly higher at lower pressures. What you end up doing is you end up actually carrying a huge quantity of water from the interface area along with steam. The broad thumb rule is for every drop in 1 bar of the rated pressure, I mean 1 bar lower operating pressure as compared to rated pressure, you deteriorate the dryness fraction by 1.5%. All this wet steam that
Okay.
gets carried away, for which you've actually spent fuel,
Sure. Sure.
gets drained through the mainline traps. Uh, and in most plants, we don't recover mainline condensate, so it's a waste. It's an energy that is wasted. It's treated feed water that's wasted, and wet steam will have water hammer. It will result in the walls leaking. It will result in flanges and gaskets being actually damaged over a period of time. So you have loss of fuel and you have a very high maintenance and nuisance value attached by running boilers at lower pressures.
So if I just get the construct right, you're saying that we need to then operate the boilers close to its rated capacity as far as pressures are concerned. And also in terms of capacity, you may mention that they should be at close to 80% of the loading at all points of time. But then one question which crosses my mind is that would it make sense to then buy bigger boilers which have higher heat transfer area, they have more space which can occupy steam? What is your thoughts on that?
Yeah, I mean, by that definition, are the Lancashire boilers,
Sure.
which were very close to the Industrial Revolution, which were probably the largest boilers
I
by
studied them
size.
in the textbook, so
Yes.
thanks for reminding me of that.
So,
Very nostalgic. Yep.
and with the highest water volume, with the highest heat transfer
Sure.
area, should have been the more efficient boilers. Are they
Okay.
really? They were the most inefficient boilers. So, so
Right.
the connection between heat transfer area, water holdup, and efficiency isn't true. Higher water
Okay.
holdup, a higher heat transfer area helps, but that doesn't necessarily relate and directly translate into efficiency.
Sure.
A
I
higher
get your
water
point.
holdup will result in a sluggish response. A higher heat transfer area helps in reducing stack losses, but at the same time, one has to remember that it also results in higher radiation loss. It
Sure.
also, a higher water holdup means a longer startup time because you're just heating a large tank of water. So,
Sure.
process engineering of boilers and sizing of the boiler is very proprietary to a company.
Yes.
Heat exchangers in the form of plate heat exchangers got to like 1/80th of the original size of the last shell and tube type heat exchangers. Boilers have also reduced. So it is translating into a better heat efficiency, a better design. So a volume and size of the boiler necessarily doesn't talk about its efficiency and hence fuel consumption. Uh, they are much unrelated, while some elements will be related.
Sure. So if you look at this whole logic of boiler efficiency, and there are tall claims which are made by most equipment manufacturers who operate in this space. But when it comes to reality, there is always that gap where the users always claim that I'm not able to generate steam at the rated efficiencies which are claimed on paper. What do you think is the reason, and is there any mitigation? How does it play a role in terms of sustainability? Because that's a KPI where we look at, what is the steam to fuel ratio. All these are important factors, right, in a process plant. So how does this whole role of boiler efficiency on paper and in reality play a role in sustainability?
Good question, and most can relate to it. When you buy a vehicle,
Okay.
you buy as per ARAI standards,
Oh, sure.
your mileage and fuel efficiency, so and
Absolutely.
so. So I won't blame the equipment manufacturers. They also claim that as per ASME PTC or BS standards, these are 845, these are my boiler efficiencies. So there are, but however, when you look around, you see there is about, for solid fuel fired boilers, there's about between 15 to 20% gap between rated and operating efficiencies. For oil and gas fired, it is about 6 to 8% or more. Now, there's a reason. So,
Okay.
why this gap? And should there be a gap? In ideal condition, the gap should be minimalistic.
Absolutely.
And when you say minimalistic, the practical gap for solid fired boilers should be between 3 to 5%. And for oil and gas fired boilers, it should be between 1 and 2%. But then, where are these large tens of percentages of losses going? If I split the boiler efficiency into three parts,
Okay.
uh, the three parts are one, which is something that the user cannot control. The losses
Sure.
that are incur in and which result in loss of efficiency, something that the user cannot control. That's a
Right.
deviation from standard design parameters.
Absolutely.
The second half is about the technology employed, and the third is about operating practices. So you can actually bucket the mitigation plan into three halves. Something which you cannot control, you cannot mitigate.
Right.
And what is that? Let's take solid fuel fired boilers. There's a large piece over there which is enthalpy loss.
Yes.
And typically it'll be around 6 to 7%. Enthalpy loss is on account of two reasons. It's because of moisture in the air, what's the humidity, and it's about what is moisture in the fuel. Both of this you cannot control. And why does this loss occur in the first place? Because when you put ambient air in,
Sure.
it gets heated up. When it
Yep.
gets heated up, the moisture, which is in the form of liquid form, evaporates into gaseous form. It takes away the heat. The moisture that's there in the fuel, which is in the liquid form, evaporates into gaseous form. It takes the heat from combustion, so it's a net loss. So enthalpy loss, and there's a third element to it, which is the conversion of hydrogen to moisture or hydrogen to H2O as a result of combustion, which also you cannot control because it depends on hydrogen in the fuel.
Sure. Sure.
And
Yep.
there is a specified level of hydrogen which is there as a part of the fuel, which too you cannot actually define. There is a precondition that is defined. As a result of this, this is one loss which you cannot control. There's another loss which is not a part of these standards, but it's part of operating, which is the blowdown loss. If you simply do not have water available with zero TDS, and if
Yes.
you are putting water with high TDS, you have to drain it via blowdown a certain percentage. So, as a thumb rule, for every 10 ppm increase in the TDS in the feed water, you lose on efficiency by 0.3%.
Okay.
Ambient temperatures. If I'm running in Rajasthan in summers where my ambient temperatures are 40 degrees, vis a vis, I'm in some cold country where my ambient temperatures are sub 5 degrees, or the variations between afternoon, morning, evening temperatures is out of your control, because the temperature difference of the boiler after insulation and the ambient would decide the radiation loss.
Sure.
That too is not in your control. So, parameters which are out of your control, you cannot mitigate, because the efficiency claimed by the manufacturers bases
Yep.
certain standards and
Sure, sure,
assumptions that are
sure.
made. Things that are in your control, which is now technology. Boiler is a slave of the process. If
Absolutely.
the demand goes up and down, the boiler has to respond to it. So, like how a accelerator accelerate, when a vehicle you accelerate, in a boiler you also try to accelerate
Sure,
fuel throughput.
sure.
And when
Yes.
you accelerate fuel throughput, like how a carburetor or a fuel injection system in an engine does, where it controls very finely the fuel and air input, same in boiler, the combustion system is expected to actually control and have a very stable air to fuel ratio across the range of operation. That is something that is in the control of technology. And I'm saying it's in your control because you make a choice while buying a boiler what technology I want to employ.
Okay.
So if you do electronic compound regulation, if you do oxygen trimming systems, if you have a modulated and regulated air and fuel control through automated air dampers based on solid fuel gas firing, and maintain a constant range of excess air, because stoichiometric air will be dependent on fuel
Sure.
properties, but the excess air will be based on the load and how well you're controlling. And if you're able to control that, the technology employed there will ensure your stack losses, which is
Sure.
one of the significant losses, are very much in your control. The second element of technology is the quality and type of insulation that you do.
Okay.
If you do a high quality insulation, the right thickness, you can contain the radiation losses less than 1%. How much external refractory do you use? If I use a huge amount of brick wall, it's going to act like a black body and it's going to radiate the heat from combustion in all directions, resulting in a huge loss. So these are some elements of technology which you can control. The previous question that you asked, am I operating the boiler close to the rated pressure, is something that you can control, which indirectly impacts the boiler
Right.
efficiency. Coming to steam to fuel ratio, which is a derivative of boiler efficiency,
Absolutely.
am I returning enough condensate to improve the overall steam system efficiency, are things in your control. Now, coming to the
Yes.
last element, I'm going to stretch a little longer, which
No, no,
is
it's absolutely fine.
operating
Very good
practices.
insights. Yeah.
Am I cleaning the boiler regularly? Am I ensuring that I'm calibrating all the motors? Am I ensuring my oxygen level and oxygen sensors, my level controllers are operating well? These are routine preventive
Yep.
maintenance practices which need to be maintained, and they have an impact. If your boiler is manually operated, you'll see, based on the operator, even a difference in the efficiency. So there are these three elements which one needs to be conscious of and really invest time, energy, and effort where it matters. While buying technology, then operating practice to actually sustain the uptime and reliability of the
Sure.
technology so that it actually delivers the benefits.
So, if you look at the whole business of looking at the efficiency of operations, then there is one thing which crosses my mind. You kept on talking about, the combustion losses, and there are stack emissions, and there are a lot of heat recovery devices which are, suggested or implemented also at times. But most often, it is seen in the industry that they are, again, like, I'll borrow your word if you are okay, that they are like white elephants. You have a air preheater or a water preheater, you have a economizer, but do they really pay back in terms of what we do in terms of investment on such white elephants, or are they just, again, there because it's a sustainability drive and you're looking at carbon footprint reduction?
Yeah, good question. Uh, they aren't white elephants, provided you make the right choice of the technology
Sure.
when you've actually installed. For example, Um, if you're having gas firing,
Okay.
economizer should be your obvious choice. You should design it for exhaust temperatures between 120 to 130 degrees Celsius. You can further improve efficiencies by doing partial condensing and going right up to 85 degrees, provided you have an application of hot water in your plant.
Okay.
Many people go for this fancy condensing economizers with claims of efficiencies between 99 to 102%. They condense the flue gases, they buy this expensive piece of condensing economizers, but now they don't know what to do with the hot water because the hot water runs into 100 meter cube per hour, 90
Oh,
meter cube per hour to actually use it, and they don't find an application. So
sure.
that's a white elephant, to give you an example.
Yeah.
If you take biomass boilers, uh, I, you should go for economizers as your first choice. But if you
Okay.
have a wet fuel, you should use a combination of economizer and air preheater and expect temperatures between 140 to 160 at the exhaust, because below that you'll start having corrosions. Air preheater heats the combustion air. It helps, it not only recovers heat, but it also helps better combustion by increasing the adiabatic temperatures in the furnace by virtue of putting 100, 110 degrees hot temperatures inside. You should not use air preheaters for gas firing, and
Okay.
also where your NOx emissions are stringent. If you use air preheaters for gas fire, it will increase the NOx level substantially, and so for biomass or coal-fired boilers. So
Sure.
you have to have take a prudent decision in terms of environment, in terms of operating loads. If you know your boiler is going to always run
Mhm.
at below 30 or 40% of the capacity, the air preheater or the economizer or any other heat recovery unit will not do any good except for causing corrosion and leakages and more maintenance.
Sure. So coming back to the thoughts in terms of going forward in terms of boiler efficiency and its impact on operating costs, what do you think are the current trends? Where is the technology heading? What is the role of the current norms of IoT, Internet of Things? How is it panning out in this business?
So there's a lot of emphasis though, uh, but there are challenges.
Okay.
So I'll come one level below. If you are able to have good combustion systems where you're able to maintain CO levels less than 20 to 30 ppm and oxygen between 2.5 to 3.5% for gas firing, below 7.5 to 8% for typically for solid fuel fired boilers, I think you're solving one element of combustion. And of course, stack temperatures in the range that I mentioned before. There are many more variables. And the variables are
Mhm.
the gap that you have to solve is my fuel keeps changing, especially in solid fuel and not for gas. My operating practices may not be perfect because human beings have imperfections. That's where machine learning and AI come into the picture. They try to bridge exactly this gap. And they try to pick up data, not on spot basis, but on a continuous basis. And once they pick up the data, they also are analytical tools because they'll also throw up a trend and a pattern. So they will link it with multiple variables like what is the load on the boiler,
Sure.
what was the type of fuel, um, who was the operator, when was the last preventive maintenance conducted, and what could be the probable reasons of why the boiler is not operating efficiently. So they throw up gaps. They throw up gaps for human beings to address them proactively by looking at the output and sustain efficiencies.
Sure.
The next level is going to be, which is now happening in AI, which what we see with Chat GPT, etc. I was the other day, I was on a Google Meet and it actually took complete notes of the meeting,
Yep.
and that removed human intervention completely.
Absolutely.
And that's another stage where the boiler becomes completely independent of human intervention, which means that it captures all the variables, tweaks itself to make it least or zero human dependent for any corrections. So it analyzes data on itself and takes its own corrective actions. And I see that to happen over the next 5 years, uh, as the sensors get more established, as the algorithms and our understanding of the factors and interdepending factors actually become more and more clearer. And for this to happen, one would need hundreds of boilers that are connected,
Sure.
which are capturing a lot of data, and you allow these tools to form their own algorithms with a self-learning basis, so that they come up with this output where they can run the boilers, and the boilers can run themselves in the most efficient way.
Excellent. I'm really happy that you have given us lot of insights, lot of good thoughts which we can take forward. Just to sum up, I would say that there are so many thumb rules which you actually were trying to give to us, and I'm sure that if we go through your inputs in terms of three parameters which you spoke about, one is to really look at what is that which I have to do when I select the right steam generator. Second, what are the parameters at which I'm supposed to operate and maintain this whole technology which I buy at a premium cost? And the third point is to really look at what is the role of AI, machine learning, which will enable me to sustain these parameters and really look at a better carbon footprint reduction and operating cost benefit. It's really amazing to have you with us at the podcast. Thank you, Vivek.
Thank you, Vaibhav.
So, thank you for watching the FM Energize podcast. I'm sure there are a lot of learnings for us to take forward. Please do subscribe to the podcast. Thank you.